Okay friends, today lecture 6 on linear programming problem. So let us discuss some problem. A catering agency has two kitchens to prepare food at two places A and B. From these places, midday meal is to be supplied to three different schools situated at PQR. The monthly requirements of the school are respectively 40 and 50 food packets. A packet contains lunch for 100 students. Preparing capacity of kitchens A and B are 60 and 70 packets per month respectively. The transportation cost per packet from the kitchen to school is given below. Transportation cost per packet in rupees. So A to P 5 rupees, from B to P 4 rupees, from A to Q 4 rupees, and from B to Q 2 rupees, and from A to R 3 rupees, B to R 5 rupees. Now problem is how many packets from each kitchen should be transported to schools so that the cost of transportation is minimum. Also find the minimum cost. So this problem is called transportation problem. So we have to minimize the cost of transportation by using linear programming. Let the number of packet sent from A to P equal to X and the number of packets sent from A to Q equal to Y. So a catering agency has two kitchens to prepare food at two places A and B. So we have kitchen at say place A and second place B. And after preparing foods, midday meal, we have to supply it to three different schools situated at PQR. So this is school P, Q and R. So number of packets sent from A to P X and number of packet sent from A to Q is Y. And the preparing capacity of kitchen A and B are 60 and 70. The preparing capacity of A is 60 and preparing capacity of B is 70. So we already sent X packet from A to P and Y packet from A to Q. So we have to send a remaining packet, that is 60 minus X minus Y to R. It means all the 60 packets of A distributed to school P, Q and R. Now from B, school PQR, the monthly requirements of school are respectively 40, 40, 50. So requirement of P is 40, requirement of Q is 40 and requirement of R is 50. So school P already get X packet, so remaining 40 minus X packet will get from kitchen B. Similarly, school Q get Y packet from A, so remaining packet 40 minus Y will get from kitchen B. Now, rest packet of B will be sent to kitchen R, and that packet will be 70 minus 40 minus Y minus 40 minus X. That is X plus Y minus 10. So X plus Y minus 10 packet will be sent from B to school R. Now the transportation cost is also given from P to A, from A to P is 5, from A to Q is 4, and from A to R is 3. From B to P is 4, and from B to Q is 2, and from B to R is 5. So total transportation cost means Z, we have to minimize the, so total transportation cost will be 5x plus 4y plus 3 into 60 minus x minus y plus 4 into 40 minus x, 2 into 40 minus y, and 5 into x plus y minus 10. So 5x plus 4y plus 3 into 60 minus x minus y plus 4 into 40 minus x plus 2 into 40 minus y plus 5 into x plus y minus 10. So after simplification, 5x minus 3x minus 4x so 5x minus 3x minus 4x plus 5x, so x means 3x. Now 4y minus 3y minus 2y plus 5y, so 9y minus 5y So plus 4y. Now plus 180 plus 160 plus 80 minus 50, so equal to plus 370. So total transportation cost is 3x plus 4y plus 370. We have to minimize the subject to constants, subject to the constants x plus y less than equal to 60 and x plus y less than equal to 10 and x plus y greater than equal to 10, because x plus y minus 10 is greater than equal to 0. So we can send, so from B to R we send x plus y minus 10 greater than equal to 0 and x less than equal to 40. We sent x packet from A to P and P have maximum capacity 40. So x less than equal to 40 and y also less than equal to 40. And obviously number of packet will not be negative. So finally, so formulation of LPP as minimize z equal to 3x plus 4y plus 370 subject to the constants x plus y less than equal to 60, x plus y greater than equal to 10, x less than equal to 40, y less than equal to 40, x greater than equal to 0, y greater than equal to 0. So we have linear constants x plus y less than equal to 60, say first, x plus y greater than equal to 10, say second, x less than equal to 40, third, y less than equal to 40, fourth. So associated equation for first, second, third and fourth are x plus y equal to 60, this implies x by 60 plus y by 60 equal to 1, x plus y equal to 10, this implies x by 10 plus y by 10, x equal to 40 and y equal to 40. Now draw the graph of these equations 10, 20, 30, 40, 50, 60, 70, 10, 20, 30, 40, 50, 60, 70. So for first equation, x by 60 plus y by 60. So x intercept 60 and y intercept 60. X plus y equal to 60. Second equation, x by 10 plus y by 10 equal to 1. X equal to 40 is a line parallel to y-axis. And y equal to 40 is a line parallel to x-axis. So by origin test, for one, origin means 0 plus 0 equal to 0 less than equal to 60 is true. So for one, origin belongs to solution region. Origin test, 0 plus 0 equal to 0 greater than equal to 10 false. For second, origin doesn't belongs to solution region. So feasible region so x plus y equal to 10, origin doesn't include, and for x plus y equal to 60, origin include, and y less than equal to 40, it means below the line, and x less than equal to 40 means left side of the line. So feasible region and this is x greater than equal to 0, and this is y greater than equal to 0. So feasible region will be this region, and corner points of this bounded feasible region is this. So its fair graph is like this. So we have corner points, 6 corner points, A 40 20, B 20 40, C 0 40, D 0 10, E 10 0, and F 40 0. Since feasible region is bounded and convex, feasible region A, B, C, D, E, F is bounded and convex. So minimum value of z equal to 3x plus 4y plus 370 exists at corner points, and corner points are A 40 20, B 20 40, C 0 40, D 0 10, E 10 0, and F 40 0. So value of z equal to 3x plus 4y plus 370 at corner points ZA equal to 3 into 40 plus 4 into 20 plus 370 equal to 570. Z at B three into 20 plus 4 into 40 plus 370 equal to 590. Z at C 3 into 0 plus 4 into 40 plus 370 530. Z at D 3 into 0 plus 4 into 10 plus 370 equal to 410. Z at E equal to 3 into 10 plus 4 into 0 plus 370 equal to 400, and Z at F 3 into 40 plus 4 into 0 plus 370 equal to 490. So Z at E is minimum. Since feasible region is bounded and convex, so Z at E equal to 400 will be the minimum transportation cost when 10, 0 and 50 packets are supplied from A and 30, 40, 0 packets are supplied from B to school at PQ R respectively. So we can minimize the transportation cost by using the concept of linear programming. Now another problem, this problem is related to postal services. The postmaster of a local post office wishes to hire extra helpers during the Deepavali season because of a large increase in volume of mail handling and delivery. Because of the limited office space and budgetary conditions, the number of temporary helpers must not exceed 10. According to past experience, a man can handle 300 letters and 80 packages per day on the average, and a woman can handle 400 letters and 50 packets per day. The postmaster believes that the daily volume of extra mail and packages will be no less than 3,400 and 680 respectively. A man receives rupees 225 a day and a woman receives rupees 200 a day. How many men and women helps should be hired to keep the payroll at a minimum, formulate an LPP and solve it graphically. Let the number of men hired per day equal to X, and the number of women hired per day equal to Y. So according to question, we have to how many men and women helpers should be hired to keep the payroll at a minimum. So we have to minimize the cost. Minimize Z equal to 225X plus 200Y, subject to the constants the number of temporary employee helpers must not exceed 10. So X plus Y less than equal to 10. Now, a man can handle 300 letters and 80 packages per day, and women can handle 400 letters and 50 packets per day. So 300X plus 400Y and total the daily volume of extra mail and packages will be no less than 3,400 and 680. So 300X plus 400Y greater than equal to 3,400, and number of packets so men can handle 80 packets per day and women can handle 50 packets. So 80X plus 50Y the daily volume of extra mail and package will be no less than 3,400 and 680 respectively. So this is greater than equal to 680. So this can be written as 3X plus 4Y greater than equal to 34 and 8X plus 5Y greater than equal to 68, and number of men cannot be negative, number of women cannot be negative. So in this way we can formulate the given problem as LPP. So finally the formulation of the problem like this. Now, the linear constants are 3x plus 4y is greater than equal to 34. 8x so x 34 by 3 plus y 34 by 4 equal to 1, and 8x plus 5y is greater than equal to 68. This implies x by 68 by 8 plus y by 68 by 5 is greater than equal to 1. So, associated equation for 1 and 2, x 34 by 3 plus y 17 by 2 equal to 1, and x 17 by 2 plus y 68 by 5 equal to 1. So, when we draw the graph of these two lines, we will get, and one constant, that is x plus y is less than equal to 10. So, this is first, this is second, and this is third. So, x by 10 plus y by 10 equal to 1. So, when we draw the graph of these three equations, we will get the graph of these three equation of line which intersect at one point P64, means all these three lines are concurrent lines. So, the feasible reason, here the feasible reason for all these three constants in equation is a point only, because all the three lines are concurrent. Since all the three lines are concurrent at P64, so feasible reason will be .P64. So the value of Z equal to 225 into 6 plus 200 into 4 equal to 2150. So payroll is minimum rupees 2150 per day when 6 men and 4 women are implied. Now let us take another problem. This problem is related to construction activities. The standard weight of a special purpose brick is 5 kg and it must contains two basic ingredients B1 and B2. B1 costs rupees 5 per kg and B2 cost rupees 8 per kg. Strength consideration dictate that the brick should contain not more than 4 kg of B1 and minimum 2 kg of B2. Since the demand for the product is likely to be related to the price of the brick, find the minimum cost of brick satisfying the above condition. Formulate this situation as an LPP and solve it graphically. Let the weight of ingredients B1 equal to x kg and the weight of ingredient B2 equal to y kg. So ingredient we have two ingredients B1 and B2 and weight in kg is given as x, let x and y we have already taken, and cost per kg in rupees 5 and 8. So we have to minimize the cost, find the minimum cost of brick satisfying the above condition. So x plus y weight the standard weight of a special purpose brick is 5 kg. So x plus y equal to 5 and the cost function z equal to 5x plus 8y. And condition on x, the strength consideration dictate that the brick should contain not more than 4 kg of B1. So, condition on x is x less than equal to 4 and minimum 2 kg of B2 and y is greater than equal to 2. And obviously x greater than equal to 0, y greater than equal to 0. So, formulation z equal to 5x plus 8y, this has to be minimized subject to x plus y equal to 5, x less than equal to 4, y greater than equal to 2, x greater than equal to 0, y greater than equal to 0. So, when we plot the graph of these three constants, we will get the graph like this. So, x plus y equal to 5, x less than equal to 4 means left of x, y greater than equal to 2 means above y. So, when we are considering all these three conditions, we will get the feasible solution on line AB only. So, feasible reason for this linear programming problem is a line. It means all the points on this line will give the solution, but we have to find exact minimum value. So, the corner points of this feasible region will be AB, corner points A 0, 5 and B 3, 2. A 0, 5 and B 3, 2. So, Z at A is equal to 5 into 0 plus 8 into 5 equal to 40 and Z at B equal to 5 into 3 plus 8 into 2 equal to 31. So, Z minimum equal to 31 at B32. So, weight of B1 equal to 3 kg and weight of B2 equal to 2 kg. So, in this way we can use the concept of linear programming problem in construction activities also. So, okay friends, now we discuss various types of problem in linear programming problem. Okay, thank you.